Hello, everyone. My name is Jordan Padams from JPL, PDS Engineering Node, also known as the Jacket Guy, thanks to Trent on the first day. I wasn't sure if I was going to wear the jacket today, but I had to now. But anyway, I'm going to talk to you today about the PDS Search API. So some quick background. So a lot of you in the room, probably everyone, knows about this PDS-4 information model, right? So it's this architectural approach that was developed to support planetary science and this highly diverse set of heterogeneous data, right? So we have all this data from all over the place, right? We have orbiters, rovers, lots of instruments on each one of them, all this different science disciplines, right? Across all these different, and actually located in all these different places all over the world, right? So how do we then take this data and we actually try to make some sort of information model that made sense, right? So we have the architecture, which is software and the relationships of the data. We have the standards, the schemas, all the other stuff, right? And then that basically gets passed over to the archives. So that is here in the United States, we have the PDS, we have PSA, we have JAXA, all these other archives where we take the data, collect it, archive it, and access and provide access. So we have these archives, right? PDS-4, like I just said, all this data coming in from all these different places, all these different spacecraft. And it's luckily, supposedly it's in PDS-4. So it's supposed to be somewhat consistent, right? We have these consistent formats, these consistent metadata, right? So if you think about that consistent metadata, you can build these APIs much easier, right? Because you're not thinking about, oh, Cassini called it one thing, but Galileo called it another thing. Or these missions in PDS-3, right? They came with these keywords that are actually the same name, but meant something different, which is impossible to know unless you are on that mission, right? Well, now we have a well-defined standard. We can provide well-defined APIs. And then from there, we have this consistent API across not just at NASA, not just at PSA, but across everyone, right? Same API access point, where now you, the community, can build your tools and services to use this API, right? You no longer have to know where the data sits so that you have, okay, it's at this node or this archive. I need to develop that. Oh, that API does this. Oh, but this API is different, right? You don't have to develop 8 interfaces. It's just one, right? So you can develop a client, you can link back to the PDS more easily, right? So you have derived products. You can say, I use this thing over here. Okay, perfect. Just give it to the API, right? So you can see it provides a lot more end-to-end accessibility and discoverability of the data, right? You can see where this picture starts to look more clear and more together versus just kind of this disparate system, right? So the centralized search API for planetary science, it's crucial, right? It's crucial to making this your lives easier. Honestly, in the end, the whole point is to make your lives easier and future scientists' lives easier. Okay, so re-intro, because I've presented this a few times in various venues, but just our API, what you can do with it, right? So we have endpoints to do a few things. One, you can search for bundles, collections, or any PDS product using advanced search queries. So by that, I mean, you can think of any search queries you do into APIs, but also to Google even, right? They have their complex query language you can use. This is just an example. We borrow straight from the information model, right? The attributes that we have here. So you see start date time as an example. We just map it using this dot notation to actually query the API, right? This is a very simplistic example. We're going to have a demo in a few minutes that's going to show you much more details, but that's one example of just a way you can query something very specific that's in a label, how it ties, and that is consistent across the entire system, right? So you think of every data product in the system, this is exactly how it's done, it consistently, right? So it's adding this level of consistency again to the system. Two, query parameters. Again, these are just screenshots. You can find this online. The next thing you do is you can browse the archive hierarchically. So we have, for those of you that are aware, in PDS-4, we have bundles, collections, products, right? And sometimes it's interesting. You want to start a lot of the time actually at this data set level, right? This higher level. You don't know necessarily what you want. So you want to be able to browse, right? So now we have this ability to kind of do this, right? Go up and down, where I'm a product. I kind of want to know what bundle this belongs to because I want to know the documentation that's related to it, right? You can now start to put these questions together, right? Build software, build tools around it to say, what's related to this and how can I figure out where this fits in the system, right? So you can now ask the API these questions. Here's the API spec, right? It's in a lot of details, but we use this term member of, right? You can kind of think of in a relationships. It's a member of. So that's what we use here for products. So you can search and, again, browse up and down. So last point is you can resolve an identifier, right? Fun fact about the PDS, there is actually nowhere in the system you can go and just find a product, right? You can't go anywhere right now to actually say, I know this product. I literally have the identifier. You have to go to 8 different places to find it. And so now we can at least provide a mechanism where you can immediately go and find one product across the entire system, right? And so this is curl. So, for all you curl fans out there, specific example of just searching for a, this is an Insight RAD bundle, right? I know it, and now you can get the metadata back. You can find that bundle in the system. So here is another thing that we have. We have various response formats that you can use. Application JSON, XML. We have these PDS4 specific ones as well. Play around with them. I'm not going to get into details here. I mean, it would be, I don't want to belabor that point. So updates since version 1. So the API has actually been online for about a year, but we've been slowly adding data to it. So we have some improved documentation online. Lots of cookbooks we're starting to build out. As we'll show in a minute, we have a demo also that can be used as kind of a baseline for using the API. We have these ops fields, quote unquote ops fields, right? Which are just metadata or metadata about the product. So it's kind of like things like the data file, right? Or the labels. If you want to know where they are in the system, you don't care where they sit necessarily, but you found them, that you have a URL, right? The file ref, you now can find any product in the system, no matter where it sits. Or like MIME types or file references, that kind of thing. So yeah, a lot of this other stuff you might not care about, but it's all there. And then we have a lot of data loaded. So right now it's only PDS4. We have 82%. I'm using the bundle number because it's higher, but I'm not lying, right? So we have 82% of our data loaded. And so that's all in there. We don't actually have a product count. So I couldn't even tell you right now how many products because we're not really sure of that. But at least from a bundle perspective, 82% loaded. That includes actually some PSA data as well. So we're now branching out beyond just the PDS nodes, but now we're starting to think, oh, we're including data from across all the archives, right? Not just the PDS, which I think is really can start to show the real power of this API. All right, and now we're going to get to the fun part. So I'm going to dive right in here to a demo. And actually, I'm going to go against the rules here. I'm going to click out of, let me go back. Click out of here. And let's see, because I want to see if anyone knows that we actually have a YouTube channel. Oh, maybe I'm going to fail at this. Oh, Windows machines, I don't know what I'm doing. Okay, there we go. Yeah, see, I don't know. I don't know what's happening when I go on these other things. All right. This is the real demo, actually, is just seeing if I can do this. Oh, didn't even copy it. That's nice. Sorry, just excuse the delay. All right, so we go to our notebooks, which does exist, right? So it's online. We're going to go to our video here. And then, yeah, so this is actually not me. So it's going to sound not like me. This is Tomas Lebreu, who is our dev lead down here. So if you have any questions, you can ping him about it. But yeah, so we'll take it away with the demo.
In the video, we're going to show you how to request the PDS search API from a Python Jupyter notebook. The material for this video is publicly available in this GitHub repository. You can run this demo and elaborate from it by following the instructions which can be found in the README. But for the sake of time, I already started Jupyter Lab and installed all the dependencies. In this notebook, we want to visualize spectrometer observations of the asteroid Bennu. We are first importing the dependencies, matplotlib to plot the observations, and AstroPy to read the fits data produced by the spectrometer. We then import this API client library that we provide to read from the web API. We need to configure this API client library with the URL of the PDS API. We're doing that here. And then we want to get the properties which describe the OVIR's spectrometer dataset. For doing so, without a priori knowledge of the description format of these products, we simply do a free text search on OVIRs using the keyword argument of this method. In the summary of the response, we can find the properties which describe the OVIR's product. As a reminder, the PDS API is transparently exposing the PDS4 information model descriptions of the product. What you can see here are the dot notations of the PDS4 properties. The properties we are specifically interested in for this demonstration are the data file reference, where we are going to read data from, the coordinates of the observations to select a specific location on the asteroid Bennu, and the range, the target range, the distance to the asteroid Bennu, so now let's extract the data set that we want for this use case. We want to get the observations around a specific location, this latitude and longitude, and we want to get observations closer than 4 kilometers to Bennu. We're going to use this method product list again, but this time with the Q equal argument. This Q equal argument enabled to have complex queries. And I will show you on this example what the possibility we have here. So we want to get the observations made on the asteroid Bennu. We're doing that with target equal Bennu 2 minutes. Knowing is a lead identifier. We want to have observations made by the instrument OVIR. Instrument equal OVIR as a lead again. We want to get observations closer than 4 kilometers, lower than 4 kilometers to the target. And we want to have observations targeting a specific location on Bennu with this bounding box from 9 to 15 degrees of latitude and from 21 to 27 degrees of longitude. We're using these criteria to filter the products we want, and then we're going to filter the properties we want to get for this product. And specifically, we want the data files in these properties. I'm going to run this query. And we're getting the result in the data field of the API response, this time in the variable closer products. So let's look at how many products we got. We got 4 products. Each of them is an object defined in the API client library. that we can plot, that we can print as a dictionary. So this object is contains metadata on the dataset, and specifically the properties we requested, among some others that are here by default. But we can see the one we want, the feeds file, the URL to the feeds file, the latitude, longitude, and target range, which value match the request criteria that we have. Now, to plot the data, we want to extract the...
Sorry to end on a cliffhanger
okay.
here.
You can either go get your cookies or you can keep watching the rest of it. How about that? So we'll let everyone do that. If you're not interested, feel free to take cookies. There is 1 minute and 30 seconds left. If you really got to get out, go for it.
To the feeds file, we're doing that with this block. For each product in the result, we want this property, and we have a set of 4 URLs to feeds file. We can easily plot these files using the AstroPy library to read the files and matplotlib to plot each of the observations. We can see on each of the detectors of the spectrometer instrument the 4 observations of this location on Bennu asteroid. This is it for the demo. I believe this is an
All right, that's it. Thanks, everybody.
Thank you very much. Okay, obviously we have no time for questions, but please give a hand to all of our speakers for this afternoon's session, and then we'll see you back here at past.